Have you ever seen a 3D printed part with a cool interior structure, some futuristic lattice which makes a part light without compromising its strength? If you wanted to create this, then you would have had to buy an expensive CAD package. I've designed a geometry node based tool for Blender which lets you do this. It is available over on Blender Market right now. This tutorial will show you how to use it. So I do a lot of 3D printing work, and I often use Blender to model and prepare a design for 3D printing. However, Blender has lacked a number of tools, which has meant that I often had to export a model out of Blender, perform some task on it, and then import it back in. The biggest task involved altering a model so that a 3D print used less material. So after a few different attempts, I came up with an SDF based method which allows hollowing and lattices to be added to 3D prints. This tutorial will cover the basic use of the tool, which will cover about 90% of customers' uses. There are more advanced ways to combine and use the elements for other uses, but I'll keep it simple for now. To use these tools, you will first need to download the up-to-date blend file from the product download page on Blender Market. Once you have that blend file, you can either use the nodes directly within the file, or you can append the node tree into your working file. There are a lot of nodes in the folder, but for this tutorial the one you need to append is the Lattice modifier all combined file. This will bring in all the other nodes that you will need for the tutorial. With your target object selected, you need to click the Add Modifier button and select Geometry Nodes. Then you can select the Lattice Modifier All Combined option to bring up the modifier tool options. Again, there are an intimidating number of options, but in reality the task you are likely to use it for only uses a few of them. Some things to keep in mind first. The units are dimensionless, so a value of 1 means one of whatever units you have Blender set up to. I mostly work in one Blender unit to 1mm scale and design the tool around that. Just keep it in mind if you need to do any conversions. If you're used to Blender adding a modifier and doing something straight away, then you might be confused as to why nothing seems to have happened. This is because the hollow option is set to original object. I do this as there are some settings that can cause Blender to freeze if the values are too far off. The main value to be aware of is the voxel size. This is a fundamental value in making the hollow and lattice mesh work. Too large and the mesh will be too blocky, but too small and the calculation takes far longer without any improvement in quality. I tend to keep the value somewhere between 1 to 200 voxels can fit within the object's longest axis. It's usually much better to work with a larger voxel and then refine it than to do everything at a small size. Ultimately, it depends on your system as to how far you can push this. The second value that can really slow down the process is the cell size. This affects the size of the lattice. If the cell size is too small, then you'll have a very large number of lattice elements to calculate over. So warnings out of the way, let's begin with making a simple hollowed and lattice part. The part I'm working with is a simple cube 100 units on the size. Let's say I want to make a 2mm thick hollow with a primitive cubic lattice inside it. So it's best to set the values now and then activate it by changing the hollow option. Otherwise it will want to do the whole calculation process with each option change. So the lattice is set to cubic type by default. There are a number of options in there which I'll cover in later tutorials. The cubic type isn't the actual lattice itself, but the type of lattice. There's a wide range of lattices that can fit within the cubic lattice family, some of which you might remember if you took chemistry classes on crystals. For now though, we will stick with the primitive cubic option. Let us keep the cell size at 10, but increase the lattice element diameter to 2. This will be the default size of the wires that make up the lattice. The diameter should always be larger than the voxel size, otherwise the wires might not appear properly. Let's then increase the hollow thickness to 2 as well. This will be the wall thickness of the part. That's it now for the values. All these other options can be ignored. A number of them don't even work with the cubic lattice type, but unfortunately Geometry Nodes doesn't have a way of hiding them right now. Hopefully a new updated Blender will give the option. So the final thing is to change the hollow options to put the mesh plus lattice. After Blender thinks for a few seconds, it should be responsive again. However, you can't see anything as everything is inside the mesh. A simple way to seeing this is pressing Z and selecting the wireframe, and there it is. If you want to have a better look inside, you can add a Boolean modifier and cut off part of the wall. So now might be a good time to play around with the different cubic lattice types and the smoothing options. There are some basic cubic lattices, such as the body-centered cubic and the diamond lattice. There are also some more complex structures, such as the Kelvin structure and the Weyr-Phalon structure, which have interesting properties. There is also a custom cubic option in the lattice type. This lets you design a specific wireframe structure and use that as the basis of the lattice. This could be useful for making structural metal materials. Beyond the cubic structures, there are a number of other ones. I'll go into greater detail in later tutorials, but briefly they are the stochastic. This creates a Voronoi cell type random structure. This is good for bone-like structures. Generally it looks really cool, especially when it has a high smoothing value. The TPMS structures are short for triply periodic minimal surfaces. These include structures like the well-known gyroid. For now, the thickness of these parts is determined by the TPMS value and not the thickness, so keep that in mind when using it. There is also the custom lattice option. This will take a wireframe object and use it as the basis for the internal structure of the part. This is not arrayed like the normal lattices, but lets you specifically define where the structure element should be. Further down we have some more advanced options. The shell removal allows you to remove parts of the wall whilst not affecting the lattice. You can use this to put holes for resin or powder removal. Here there are options for how the hollowing operation works. I developed a simple and a complex solver. The complex solver allows non-ideal objects to be hollowed, for example objects with small holes in them. Here is an option to remove small hollows, which means it can remove small hollow regions in the part. It's useful for preventing issues like resin getting trapped within voids of resin parts. The lattice modification option is a useful tool if you want the lattice elements to be thicker or thinner in certain regions, or smoother. This is useful if you want to optimize the structure so that you have more material where you need it. Briefly, we'll look inside the node group itself. It looks a lot more complex than it really is because of all the different options. Any particular setup only uses a fraction of this. The real power of the system comes from knowing how to combine elements to get the effect that you want. If you append the simple implementation node tree, you will see a simpler setup to achieve what we previously did. In further tutorials, I'll go into some of the other options available, as well as show how it can be used for less obvious reasons. Let me know what you might want to use it for in the comments.